Hello everyone, welcome back to our discussion about quantum mechanics. In the previous section, we were talking about the historical perspective and introductory part of that. Now, in this part, we will go on and discuss some conceptual hurdles and the beginnings and the foundations of quantum mechanics, if you will. So, in the previous video, we were discussing about interference and how waves and particles show very distinct kind of behavior. Now, let us look at a very interesting phenomenology, which as you all know is called the photoelectric effect. In the photoelectric effect, light falls on certain photosensitive materials and you see that a current can be registered when light falls on such materials. So, that is why this is called photoelectric effect. The emission of electrons and registering of current when light falls on certain materials. Now, this is a very baffling phenomenon. We were not able to understand why this is happening at all, because we are looking at light as an electromagnetic wave, and why is it that when light falls on certain materials, electrons are knocked out of it, and why is it showing this particular behavior? This is the experimental arrangement. The cathode is the photosensitive metal, the anode is our detector, and when light falls on the photosensitive material, the electrons which are knocked out, they are emitted from the cathode towards the anode, and that is connected to an ammeter which registers a deflection, which means a current is passing through. When this experiment was meticulously performed, people realized that some very interesting properties are seen. For example, if you look at this particular graph, you can see frequency and energy are plotted, and as the frequency increases, the energy of the electron is increasing. Now, frequency increase leading to the kinetic energy increase is not something we can explain using purely light as a wave. Similarly, if you plot a graph of the intensity of light incident versus the current registered by the ammeter, again you see there is a proportionality, which means as the intensity of light increases, the photocurrent also increases. Now, this dependence of kinetic energy on frequency and the current on the intensity is not something we are able to explain treating light as a wave. It took a lot of years, and eventually it was Einstein, if you remember, who figured out that light actually behaves like a particle. He used Planck's quantum theory and said that light is incident as a stream of particles called photons, and it is these photons which literally collide with the electrons and they interact with the electrons, imparting the energy to them in the collision process, and it is these electrons which are knocked out of the metal. And this is the work for which, if you remember, Einstein was awarded the Nobel Prize. So, you cannot explain the photoelectric effect by treating light as a wave. You have to assume that light is showing a particle-like property. And that is why the photoelectric effect is a very important phenomenon, and the experiment is very important from the historical perspective. Similarly, another well-known phenomenon is the Compton effect, where light falls on a stationary, say, electron, and it is scattered off, but the scattered electron and the light that comes off after scattering it off has a very peculiar relation which cannot be understood by treating light as a wave. You have to treat the incident light as a particle and look at this entire phenomenon very much like a classical collision problem between two particles. The incident light always gets scattered off with a longer wavelength, which means the frequency is lesser. In other words, it has lost some energy by imparting it to the stationary particle, the electron in this case, and that is the formula to calculate the difference in the wavelength. So, the Compton effect is another phenomenon which has to be looked at from the perspective of light being a particle rather than as a wave. So now the dilemma whether to treat light as a wave or as a particle, and put all this together with the corpuscular and the wave theory, and we see that we are revisiting the old problem, and our puzzle has now become deeper. Sometimes light is showing wave-like properties like interference, diffraction, polarization and so on. And then there are these phenomena where the experiments demand that light behave like a particle, otherwise we are not able to explain this phenomena. So is light a wave or is it a particle? Does it have a well-defined nature? To answer that question, let me ask another question. In the good old double slit experiment, what happens if we replace the light source with an electron emitting source, say an electron gun, like this? So here is the classic interference experiment. Instead of a gun which was shooting bullets or a source of waves, now I have a electrons gun. So the source is an electron gun which is emitting electrons at a constant rate, and I redo the classic double slit experiment. Common sense tells me that electron is a particle with a very well defined size, charge, mass and so on. So it should show a behavior like the classic bullets. So it should show a particle like behavior. And when the experiment is actually performed, you would be surprised that electrons are actually showing wave like behavior, which means there is an interference pattern that you can see when the experiment is performed with electrons. When the electron is passing through, it is acting as if it is passing through both the slits at once, like a wave does, and interferes with the secondary and tertiary wave fronts. This is the final nail that was hit on the duality of light, and people now started questioning the very nature of matter. If particles can behave like waves and waves can behave like particles, is there really objective meaning to all of this? Look at this particular slide. This shows the evolution of the pattern of our electrons. At this moment, let me just stop and try to look at all of this from an actual perspective of quantum mechanics in the next session. For now, we'll end our session here.